So I want to start 4-9, and we're going to talk about solving polynomials, no longer equations, but inequalities. Very, very similar to equations. So the approach is very similar. It's the very end of the problem that will change. So what did we do to solve a polynomial equation? Forget what you're seeing on the board right now. I'm going to get into this. What did we do? What were the steps taken for solving a polynomial? Maura, what do you have to do?
First, you have to look for the GCF.
Okay, before you get a GCF there. 7 equal to 0, move everything over to one side. Then, yes, look for a GCF. Good. If you have a GCF or don't, after that, what do you do? So even if you do take something out, you have to continue to factor as much as possible. So we could say that our steps are, remember, get to equal to 0 on one side, and then factor completely. Factor completely means GCF and then any other factoring technique you know. So get it equal to 0, factor it, and then we would?
You set each x equal to 0.
Correct. We set each factor equal to
that's
0,
right.
each factor, and then get the x values. Now, that's where it's going to change. After we set the factors equal to 0 with this, we're not going to call them roots or solutions anymore. We're going to call them critical points. Critical points. And we'll talk about how those play a role. And then we're going to have to use a number line and test points, and it's really actually pretty easy, but the idea is the same as what we did with polynomial equations. Let's start with this first one. So let's imagine, please, we're going to grab the solution afterward. Let's imagine that this is not an inequality. That's what you have to always start with. Make believe it's not an inequality. Get everything on one side. Okay, that's done already. Nice. Factor completely. How do I factor y squared minus 3y? What does that become when factored, Alex?
Y minus 3.
Y times?
Y times y minus 3.
Good. So this is the factored form, and I'm going to put equals 0, even though it's not equal to 0. I can put less than. Actually, I should put less than and carry down. Okay? But in the next step, what you're going to do is you're going to treat this as if it's equal to 0. And you're going to say, well, what would my answers become? It would become y equals 0 first, and then y equals 3. Those would be my answers if this were an equation. It's not. So let's write a note on the side. I usually write a note that says, I put CP on the side. These are my critical points. Critical points. And the critical points are the roots, right? They are the roots. But what we're going to do is we're going to look at them on a number line. So we like steps. We like writing down steps. Everything's been the same, but when you get to the critical points, you take the critical points and plot them on a number line. Plot them on a number line. This technique you're about to learn is something you're going to use in pre-calc and in calculus, actually, both. The idea now we have to recognize is that we want to know, and this is hard to understand, so watch where I'm pointing, please. We want to know when this polynomial is less than or equal to 0. Numbers that are less than or equal to 0 are what kind of numbers? Alex? Negative. Set of negative numbers. So I'm looking for negative answers, really. And I have 3 regions. Let's label this as region 1, region 2, and region 3. I have 3 regions because there's 2 critical points. These critical points are like barriers. You're breaking up into regions, into sections. So I've got 3 regions. What I need to do is test all 3 of these regions here. I need to test them to see if the value is indeed less than or equal to 0. How do I do that? I take a point in the region. It doesn't matter what point. A point that's the easiest to use in this region cannot be the critical point. So I can't use 0, even though that's nice. So in this region, what's a number that's pretty easy to use that's not 0? Negative 1. It just makes the most sense. Use numbers like 1, 0, negative 1, integers in general, right? So try negative 1 in the factored form. So the next step, if you're writing down steps, for those who like steps, test a point from each region. Test a point from each region in the factored form. Now, if you factored it wrong, you're going to have a problem. But we're assuming your factoring is done correctly. Test a point from each region in the factored form. When you test -1 in the factored form, do you get a negative or a positive result? If you plug -1 in here and here, what kind of an answer do you get? -1 times negative, yeah. So negative. It's okay. Just be careful of your signs. This region becomes a positive region. Notice I'm not putting the answer. All I care about is if it's positive or negative. Because originally this said, when is the polynomial negative? That's what it's asking me. Literally, this is saying, when is this polynomial negative? And when I test the point, is it negative over here? No, it's positive. Because when I test the -1, it becomes -1 times -4, which is positive 4. Test 0, oh, you can't test 0. Test 1 from this region. Put a 1 here, becomes positive 1. Put a 1 here, it becomes -2. 1 by -2 is negative, so let's label this region as a negative. I'll go through it again. I find my third region. I pick a point that's in the third region, that's the easiest to work with. 4 is the next integer after 3, so I'm going to choose 4. I can't choose 3, it's a critical point. I never choose the critical point itself. So I choose 4, I plug a 4 in here, positive. Plug a 4 in here, positive, because 4 minus 3 is 1. Positive times positive yields a positive answer. So this region is also positive. Again, I'm looking to see whether each region is positive or negative. All right, well, the problem in the beginning asked me, when is this polynomial negative, or when is it less than or equal to 0? Well, it's negative where you see the negative sign. So what I'm going to do is I'm going to recognize that this says less than or equal to 0, so I can put a closed circle here and a closed circle here. The reason I can put closed circles is because it's less than or equal to 0. Had it been less than 0, I would just put an open circle. And because the middle region is negative, I shade the middle region. So an answer for this becomes the following. Okay, my answer becomes the following. From 0 up until 3, including the endpoints. So the critical points are the same as the roots were, no different, but then I put the critical points in the number line. I test a point from each of these regions in the factored form, seeing if it's a positive or negative result. I recognize that the problem asked us when it was less than or equal to 0, which means negative, so I highlight or shade the negative region. Had the answer been greater than 0, I would have shaded over here and over here, and I would have a disjunction. Whereas now I have a conjunction. Remember, conjunction and disjunction. So this is like an AND statement. Yes?
Okay, so if the middle region was positive, then
Nothing would have been shaded. Just the 2 points, 0 and 3, would have been colored in. Because if everything's positive and we want to know when this polynomial is less than or equal to 0, no region would satisfy that. Okay, we're looking for the region that satisfies the original statement. Valentina?
No.
You sure?
Well,
Yes.
I was asked what happens if the region 3 is negative and region 1 and 2 are positive.
Oh, okay. So if this were negative over here only,
Yeah.
so then your answer would be everything greater than or equal to 3. So you would say y is greater than or equal to 3, and that's your only answer.
Oh,
Okay, so whatever region is negative goes into the solution set.
so you would never mention 0?
Well, it depends. In this case, well, for that case you mentioned, yes, the 0 wouldn't even play a role. Yeah? 3 would be the only boundary that actually plays a role. I want to show you guys where this is coming from, though. I don't want you to just take it on my word that this is right. And there's an easy way to see this. Okay, a very easy way to see this. Treat this problem as if it were x and not y. Make believe the variable is x for a second, okay? Open up your calculator, please. Go to y1. This is a wonderful technique, by the way, for those of you that want to do well in their like SAT. You take PSAT, SAT soon? PSAT, right? Okay. So if you want to improve and do better on standardized tests, what I'm showing you right now, the calculator, is a very easy way to come up with the answer without doing any work, actually, too. Okay, so let's go ahead and graph x squared minus 3x. So graph the original, but just call it an x, not a y, please. Again, graph this original, but instead I want you to graph like y1 equals x squared minus 3x. That's how I want you to put it into the calculator. I know it says y in the problem. We're going to call it x because our independent variable in the calculator is always x. When you have it in y1, please press zoom 6. Just so we can get the standard graph. I always zoom 6. Whenever I graph, literally, whenever I graph stuff, I hit zoom 6. Zoom fit is only useful when you know what your x values are. By the way, you used zoom fit the other day, right? Zoom fit does not adjust your x values, only adjust the y values. So keep that in mind that if you're not seeing two x-intercepts and you hit zoom fit, it might not find it for you, okay? So if your x-intercept is out at like 85 and your other x-intercept is at -2, you'll see the one at -2 right now, but not the one at 85. If you hit zoom fit, it will not find it. So zoom fit adjusts your y values based on what the x values are in the calculator. It doesn't change the x values. Okay, it stretches the graph this way, the window this way. When you hit zoom 6, what do you see? What do you see? What do you see? What do you see? Give me something. Give me some detail about the graph. Go ahead.
The y-intercept is 0, like it crosses. It crosses through the origin. And
where else?
And the other x-intercept is 3.
Yeah, and where do those come from? Where do the 0 and the 3 come from on the graph? You guys are all seeing, look at your graph. 0 and 3 are the x-intercepts. Where do they come from?
It will be put in the
No.
2 points that we graphed.
Yeah, the critical points. The solutions to an equation are the x-intercepts, are they not? We talked about this in class. We've gone over this now. The solutions, again, listen please, the solutions to an equation when set equal to 0 are the x-intercepts. Because this is saying, when is this equation equal to 0? It's equal to 0 here and here. But actually, ours is not saying that. Ours is saying when is it less than 0, right? Or less than or equal to. Look at the graph. When is this graph less than or equal to 0? It's in this region right there. Look at what I just drew. That's the region we care about. And then obviously it goes to be above and above. So this is really saying, ready? Watch where I'm pointing, please. Watch where I'm pointing. This is saying, when is the function below the x-axis? That's what it's actually saying. Again, I'm going to point this out if you want to write it down. This right here, this beginning part says, when is this function less than or equal to means below, and 0 is the x-axis. When y equals 0, you're literally on the x-axis. So when you're doing these problems, yes, you're going to find the critical points. Yes, you're going to put a number line. Yes, you're going to test the regions and come up with an answer based on what you're looking for. You're looking for less than 0, negative numbers. Or, if you're on a standardized test, or if you're taking the test next week here and it's multiple choice, are you going to do all this work? Absolutely not. It's a waste of your time. So for those of you that struggle with finishing tests, you need to think of quicker ways. This is one of those things right here. Multiple choice, this is all extra work. Go right into this, look at the graph. It says, when is it below the x-axis? When is that? From 0 all the way until 3. When is it below? Your answer is always the x values, the domain. It's always the x values that give the answer.
So even if instead of y it was x, it would still be when is it below?
Correct. If I change y to box right now, put a box symbol, it's the same answer. If I put a triangle, if I put a letter z, if I put the Greek letter beta, I could put any value for that variable. We always, 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 always look at the x values or the actual domain that's below the x-axis. This is always going to be the technique for these problems. Okay, yes?
Does that mean if it's a greater than it would be above that?
Correct, exactly. And notice, Regina, look, positive, everybody look up please, positive, right here, that's this positive branch. Negative, That's below the axis. Positive. That's this positive branch. That's what you're seeing on the number line. This number line is telling you the function is above the x-axis, below the x-axis, above the x-axis. And you literally see that. So for a graph that looks like this, that opens down, part of it will be below the axis, above the axis, below the axis. So in that case, you have negative, positive, negative, right? You're going to pick up on trends with this section also.
Get h squared times h minus,
Minus, yep.
yeah, minus 3, and then h minus 3 again.
Therefore, Alex, my roots are, or my critical points are what?
0 and 3.
Technically, I have a double root at 3 and 0. Do we see that? 0 occurs twice because it's h times h. So h equals 0, the other h equals 0. That's a double root. H equals 3, h equals 3, another double root. We have a set of double roots. I go to my number line to graph this. Since I've got a set of double roots, I'm only going to see 2 critical points on the number line. 0 and 3. Yeah, they're double, but you can't show it twice on a number line. Okay, you can't show it twice on a number line. This graph will be, let's see. I think they're all positive if I'm correct. This is going to be an open circle, open circle. So my answer is all real numbers except the open circle. Because we wanted to know, when is this function, for those that are a little bit lost right now, look up, when is this function greater than 0? Well, every scenario, if we try a number, is going to be greater than 0. I know for a fact that they're all going to be greater than 0, because really, what am I doing? I'm squaring something here. No matter what I plug in for h, if I square it, what is it going to be? And then here, aren't I technically squaring h minus 3? So no matter what I plug in for h in h minus 3, I'm squaring it. It's a positive times a positive no matter what I plug in, which is why all the regions are positive. So we want to know when it's greater than 0, every region. Well, except at the critical points. At the critical points, it's equal to 0. So my answer for this is from negative infinity up until infinity, but excluding 0 and 3. So you could say this. H is in the set of all real numbers, comma, h cannot equal 0 or 3. Oops, that's x. I said it's h. Okay, that could be my solution if I want to write it that way. I could write it in 3 parts. H is less than 0, or 0 is less than h, which is less than 3, or h is greater than 3. So I'll write each segment separately. Or I can write it in interval notation. There are many ways to express this answer. Okay, so again, to reiterate, I could write h is less than 0, or 0 less than h less than 3, or h is greater than 3. That's the second way to write it. The third way to interpret this is called interval, like we've said, from negative infinity to 0, from 0 to 3, and 3 to infinity. Any of those 3 ways is correct based on this problem. Any of those are correct based on this problem. Now, one thing I want to point out is what the actual graph of this looks like. So on the right, I'll draw that. It's a double root in both cases at 0 and at 3. So here's one root right here. Here's the other root right here. This graph is always going to be positive, right? Look at the number line. They're all positive. So it's always above the x-axis. It's going to come down, touch, come back up, come back down, touch, and come back up. That's the graph of this. And I know it's not like, oh, I get that right away. It's not going to be second nature yet. We're going to get to this later in the year. But I want you to pick up on stuff. Positive, positive, positive. Above the axis, above the axis, above the axis. It's always above the x-axis. These are always positive. Where you have critical points, 0 and 3, are where you have x-intercepts. The critical points were double roots. Double root, point of tangency, point of tangency. Whenever it's a double root, you'll have a point of tangency every time. It'll get to the root, and it'll turn back around. It won't go through the axis when it's a double root. Okay, really important for your graphical knowledge for this kind of stuff. So again, tonight's concept, over the weekend, 5152. On the test, you're going to be given parts with and without a calculator as always. If you can use your calculator, and it's a problem like this, I don't expect anyone to get it wrong at all, because you can check and look at the actual shape itself. So be familiar with looking there on the calculator also to check your work at least to help you. Okay? Have a good day, guys. Feel free to stay after today. If you have questions, you want to hang out, you can. I'll be here for at least an hour. And I gave you your quizzes, right? Yeah.